So my name is Akshika. Thanks a lot for making the time to join the session. So currently, I'm a lead ML engineer at Main Street Partners. It's a company in London that focus on financial sector. So we build models, machine learning models that sort of caters to hedge funds to do their trading. So yeah, so that's sort of my sort of day job. So today we'll talk about like foundations of MLOps, especially for data scientists. But obviously you can, if you're coming from a software engineering background, it'll be helpful to you as well. So as I said, myself, currently work at Main Street Partners. I'm also co-founder and CTO of Daily Kids. It's a Google UNICEF-backed startup. So there we focus on teaching kids from age 5 to 10 social emotional skills through game-based approach. So we have an app for that. So today we'll focus on MLOps fundamentals and how to sort of productionize your ML models. I wouldn't go into practicals today, so it's because like a sort of short session, but I'm happy to go into more details if you have specific questions. Feel free to ask them. So what is MLOps? So I think you might have heard this a lot in the last 5 to 6 years, like what MLOps stands for. It's basically how do you sort of bring out DevOps concept, which is concept that's coming in software engineering, how to set up infrastructure needed for your software engineering projects, and how to host your sort of apps, sort of different kinds of applications, and how do you look at the sort of infrastructure side of things. And sort of you bring those concepts into machine learning process. So that's what MLOps stands for. There's like a 60 to 70% sort of similarity between the two, but at the same time, there are like bit more nuance to sort of ML specific content in this space to do with like model monitoring, sort of retraining aspects, and like things like sort of model drift. So these are very ML specific concepts rather than software engineering specific. But at the same time, things like CI/CD, testing, these things very similar to what you have in software engineering. The type of test that you write might be different, but it's still the same concept. So as I mentioned earlier, so DevOps, where it sort of comes from, it's basically sort of the software development and IT operations side, and how do you sort of manage the life cycle of development, and how do you write like really good quality software, and sort of how do you maintain that process. So that's where DevOps sort of comes in, and you sort of draw concepts from that to ML process. So this is what the general ML process looks like, whether it's classical ML, whether it's generative AI. So this is like one way so you can sort of look at the ML process. So you would have in the middle data and model management piece where you store different kinds of input data, and as well as how you train the model. You have sort of store these information models and the metadata. It could be a model registry, or it could be a S3 bucket in AWS. Doesn't matter how you store this. You have this in the middle, and you have this like circular circular process. Not necessarily circular, but it's like a sequential process that sort of like iterates with time. So you have the ML model development piece. So you do training operationalization, and you want to do continuous training. Especially after you deploy a model, you need to make sure that the model gets retrained when new data is available, and then you do the model deployment, and then prediction serving. So whether it could be in sort of batch serving, or it could be sort of online sort of single inference that you do depending on the request that you get. And after that, it's very important to do continuous monitoring to see how your model is performing and how well, like what type of input data is that you're getting, whether it's like of the same sort of probability distribution that you're getting. So this is I'll get into more in detail later. So it's sort of continue concept called drift in machine learning, where you it's important to sort of keep track of this to identify such problems. So this is the same thing, but in a sort of sort of a waterfall kind of method that you sort of we can see. So you start with the model development piece, could be on a Jupyter notebook, that you sort of copy some sort of algorithm to train your machine learning model, and you after that you sort of create a pipeline to do the data ingestion, so data pre-processing, and to train the model, and you do the continuous training after that, where you sort of the pipeline is set in a way that whenever new data gets sort of comes in, you can sort of retrain the model, and depending on what sort of threshold that you have set, let's say you need certain data distribution that is needed to the model to get passed, and a certain accuracy threshold. So if you pass these thresholds, you can sort of then swap the new model, old model with the new model, and then you'll have a new model that is much more reliable and much more closer to the real world sort of ground truth. And then you do model deployment. So that means it could be behind sort of a API where you can sort of make requests to that model and get inference, or it could be just sitting on a model registry that you do batch processing. You do like offline processing where you don't have to have like a real-time sort of access to the model. So that's a decision that you have to make depending on your sort of use case, and then you sort of package this model and then sort of provide that as a service. So for example, if you take SageMaker and stuff, you can sort of package your model with the sort of the inference script itself. So whenever you sort of deploy this to production, you have access to the model and the script, and you can sort of easily deploy this to sort of a backend service, and any sort of application that requires this ML sort of service can access that. So that's one way of sort of doing that. So this is like very simple sort of process. So the if you can check the link that I provided, just like a white paper written by Google on this. It's slightly older, it's maybe 2-3 years old, but it's still, I think there's quite a lot that you can learn from reading that. And they have like really good like up-to-date documentation as well on this. But yeah, really good read, I would say. So this is the sort of the machine learning sort of development process, like one version of it. So there might be repetitive things that I'm saying, but still sort of we're going into more details as we go. So then, as you can see on the left-hand side, you'll have the data engineering sort of component that sort of gets raw data from the input sources. It could be CSV files, it could be emails, it could be like from some sort of API. You get this data, and then you sort of do a pre-processing piece, and then sort of convert the data to be easily used by your ML process. And also it could be, you also store your features. So that means after you get the sort of clean data, you need to do certain pre-processing, normalization, filling missing values, things like that. After you do those sort of changes to your data set that it can be easily used in a machine learning, a model training step, you can store them in a feature store, which is slightly like another database, I would say, but still this is more conceptual term as well, where a company that has like quite a lot of data scientists or ML folks can sort of maintain a centralized repository of features that they could sort of use to train models, so that it's very consistent across the entire organization when you use these kind of when you do train models. So I'll go into details in a later slide on feature stores. Yeah, I'm happy to share this. Yeah, so I will share this. And then this box, it's basically what experimentation and prototyping step, where you if you have a machine learning problem, like you define the problem in a you try to define the problem in an ML specific way, your business problem, and then you define, okay, I need to train a model to do inference, to do like if it's a prediction service, like if it's a regression model, or it's a classification model, or it's a sort of a generative AI sort of a transform or diffusion based model. So you do that, and then you do the data selection, and do a bit of data exploration, like to see like how the input data is looking like, whether it's biased. If it is biased, you need to do certain debiasing steps to do mitigate bias. If you have any questions on this topic, feel free to ask, like if something is not clear, by the way. And as I said, you do feature engineering, and in this step, you can sort of save these features, and then do the model training. So it says model prototyping. You build a model and see, and do a validation step to see if the model that you trained is good enough for your requirement. Here you would use steps, things like sort of cross validation techniques, where you sort of use 80% of the training data set to train the model, and then another 20% to test the model to see if it actually can perform, to see if the model has sort of overfit to the training data set. So you do a validation on this, and you do this like iteratively, so that to see like how do you improve the model. And you can see on the bottom there are two, like model registry and ML metadata artifact repository. So whenever you train a model, and if it's good enough, you can save this in the model registry, and even if it's not good enough, feel free to save it if you have enough space, just to keep track of your experiments. And also, like, you will store like metadata related to these models. Like, for example, if you have certain hyperparameter configurations, that means like if you take a neural network, like the number of layers, the number of hidden layers, number of neurons, things like that you sort of control in your sort of training step. You can save this information, even things like accuracy, certain distribution of input data. So that information you can store in the metadata sort of repository. So whenever somebody sort of from a different team, or even yourself, like when you check this in sort of runs in the future, can sort of verify so what went through and what were the decisions that made. So you can do like sort of a stack trace on this, and then sort of like, so these are like really good practices that you can implement in machine learning process. So highly recommended that you have this. You might not exactly do this. You might need to sort of adjust this concept according to what your organization sort of follows. So it's important that you sort of be flexible when you try to implement this, because, for example, in my organization, we use certain tools that are not specifically built for this. I mean, we use things like Grafana. Like, okay, how do you use Grafana? So you might have to change certain break the mold a bit, but still the concept is like you can store this information, like the metadata information, in a certain way, and after that you can save the code, like things like using Git, etc., using version controlling, and then because you have this sort of CSE process in place, you can sort of retrain easily whenever you do a code change or a data change happens. You can sort of you can version control the data as well as version control the code, as you're familiar with, and then you can sort of keep track how things sort of progress with time. So yeah, this is the sort of right hand side of the sort of the ML development process. Yeah. Are there any specific questions on this one before I go to?
So,
Yeah.
one thing I wanted to ask, like, how, like, have you worked with real-time feedback, and where would you factor that in?
Uh, real-time feedback, right?
Yeah.
Yeah, so I think maybe, so this is the model development process, so there's no piece in this regarding that. But if I go to the previous step, especially the continuous monitoring, the last sort of the right hand side blue box, continuous monitoring. So after you do the deployment of the model, you need to keep track like what sort of input data is coming in and how well the model is performing. So these could be stored in like sort of a log file, etc., or it could be database, depending on how we sort of implement that. And then that can be used to keep track of how your model is performing. So that's like the sort of the second stage, how to like keep track like how your model is performing.
I see. Makes sense.
Yeah, cool. Awesome. So these are some of the concepts that we'll cover through today's sort of session. Sort of continuous practices, versioning, feature stores, model registry, dependency management. I'm sure we're quite familiar with that, and containerization, infrastructure as code, orchestration. I think I need to sort of, yeah, there's a mistake. Orchestration being twice in the slide deck. Drift in machine learning, monitoring and detection in ML, environment management, testing, inference types, and also deployment strategies. Yeah, so let's get into it. So as we all know, like continuous practices is very common in software engineering. You have continuous integration, continuous delivery, continuous deployment, as well as continuous monitoring. I mean, some of these sort of slightly different from software engineering, but things like continuous integration is simply like whenever you do a change, you integrate that code, checking if the new code is breaking the previous sort of test, and sort of do that integration. And then after that, you sort of deploy this code to like automatically. So you do that continuously without sort of automatically. So I mean, GitHub Actions is a good example of this. Like there are plenty of other tools that you can use to do this. So so when you do this, like you can, like especially like with multiple people, it's very important to have this in place. Um, um, so also, like after you do, like let's say do a code change, and if you're going to do a retraining of the model, you need to like deploy the model as well, like automatically. So you don't, this like the more human step that you can remove, so it's very easy to maintain, but um it's still sort of a target rather than like sort of a place that you can get to, because there's still like, even it's very hard to achieve 100% automation in MLOps, but still you can get to 80-90% if you sort of plan really well and if you define the problem really well. And as I said, continuous monitoring, you to observe the system, uh, like how the model is performing, as well as especially for input data that's coming in, to see if there's a difference in the input data. If the input data is changing, you need to train the model, retrain the model, because your previous model would not be valid. Yeah. Versioning is basically you keep track of what is sort of changing. You can version so many things like data sets, models, code, any other artifact that's like relevant. Git is the most famous one for code, and then DVC is one for versioning data. Um, and like especially like data, it's really important like to keep track of data. So it, like if you're coming from a software engineering background, you might not sort of experience versioning data, but it's really important, like especially because that ties into your model development as well, and to see like if you want to do a retrain of the model. So it's simply like whatever, whenever you do a change, if something changes, like from a data point of view, you keep track of this. So that's why versioning is important, especially if you do a rollback to a previous model or a previous algorithm that you developed. So it's very important to do this, and sort of helps with like automated like CI/CD process as well to have this in place. Yeah. So the concept I defined earlier, it's feature stores. It's still a database, I would say, but it's unique, like a specific kind of database that has sort of data points that are sort of pre-processed, sort of, and it's curated in a way that anyone who has access to this database can train a model. This is really important. Like if you're in a large organization, you don't want your teams to um, have different features, like to create the models at different locations using the same input. So if you have, let's say, if you are working in a company that has information about, let's say, user interaction on their platform, so team A could use this information and create set of features, and team second team would use the data and like create another set of features that are all similar but still at two locations. So this sort of can introduce sort of issues, because yeah, it's always not a good practice to sort of like distribute this kind of information. So good practice is like you maintain like feature store where you have a pipeline for pre-processing data, and like whoever builds that system first will sort of publicly share that within the organization, and anybody who wants to sort of get the new data will rerun the pipeline, and you will get updated features on your sort of database, and then you can use that. This is also very helpful when you do inference, because you need to have other sort of metadata, other input data that is needed to do the prediction. So you get that from a feature. So otherwise, you'll have to sort of go to input files and like create another sort of a data frame that has these features, and that is prone for errors. So all in all, I would highly recommend, like if you're like sort of um, slightly sort of a, if it's a small organization, maybe not, but like beyond like 10 people organization, it's always good to like look at introducing a feature store, and different cloud providers uh, provide this as a solution itself. For example, AWS has a feature store, and that uses Glue database in the backend, but you can also use a standard database and sort of maintain that as a feature store. You have a specific table that has this information, and like others can sort of use that to do training and do inference. So that's just the concept behind feature store. The link that I provided, featurestore.org, feel free to check it out. It's a really good resource that you will so they look at different feature stores provided by different service providers, whether it's open source, whether it's closed sourced. They've analyzed them, provide some case studies. So it's really good to read that the website, and let's sort of have an understanding. Yeah, I think that's about feature stores. And then model registry. It's very similar to, I mean, feature store, where you whenever you train a model, it's best to sort of have this saved in a centralized location. Um, AWS has the model registry, Azure has theirs, Google has theirs. So you sort of train a model. It's basically, if I'm not mistaken, for AWS, it's basically wrap around S3 buckets. So you sort of if you don't have a model registry, you simply can save them in S3 buckets and then sort of access them. So whenever you train a model, you have like a timestamp, and you save that. You save that model so that you can keep track in the future. Like if you want to like look at like go back to like a older model, you can sort of go and to do a check on S3 bucket and get that. So model registry are really important, especially like after you train something, you need to share that within your organization. So and also you can save metadata when each run. Model registries are generally sort of built in a way to have those information saved as well. So it's good, rather than just saving a pickle file in S3. It's good to go for a model registry. These are like sort of abstracted tools of existing AWS services. If you take AWS, so like S3 buckets, like whenever you use a model registry on AWS, it's basically saving an S3 bucket in the backend. But still, it's really good, very easy for someone to like maintain like a really good lineage of the ML work that they're doing. So it's really helpful to use a model registry, and is a standard right now. To especially if you're working in a highly regularized environment, like a domain like financial sector, healthcare, it's important to you maintain this. So it's really helpful for do audit trails of different models, and to have certain information, like especially if you want to sort of deploy a model, you can train the model and sort of have it in model registry, and who's responsible, like who had the authority to deploy model, can check this, look at the metadata, and see if it's accurate enough, and check the input data sort of used in the model, and then sort of authorize this model to production. So this makes that process much easier to have something like that, and it's very intuitive if you provide the right access control for different users. So yeah, that's the concept of a model registry. Dependency management. Yeah, this is quite simple. If you're coming from a software engineering background, so you can use, I mean, Python, you'd have poetry, things like that you can sort of use to manage your environment. So this is especially if you're an analyst, data scientist, you might not understand this concept if you haven't studied that in your sort of degree. So I find it really helpful. Use these, especially if you want to like sort of have a consistent sort of development environment across different sort of users. Like for example, if you work in a like group of multiple people, and if you do changes for the same code base, it's important that you maintain the same work environment. And so Poetry is a good tool that you can use. I mean, this people have very biased views on this. It's fine. Pick whatever that works for you. I like Poetry because it sort of resolves quite a lot of dependency issues across libraries as well. So that's very helpful. Yeah, and also it's very easy to deploy if you want to like deploy that as a package. Yeah, it's an overkill compared to if using something like pip3, like pip based sort of like use like a requirement.txt file. If you're using Python sort of development environment. But if you get used to it, I feel like there's benefit to it. But yeah, you don't have to start with something like this if you're doing ML. So yeah, that's my take on dependency management. But it's really important. And if you are working with data scientists, and make sure that you get your data scientists to use dependency management, it makes life easier for you guys like software engineers, and also like everyone in the team, to have like a very consistent sort of developer environment. Otherwise you run into so many issues. Containerization, as I said earlier, is extension of what we discussed here. You'll have the sort of the environment that is needed to sort of build your ML sort of pipeline, as well as rest of the artifacts, the code, and like any other information that is needed to run independently. You sort of create containers. So Docker, Kubernetes are some of the very popular containerization tools. Like Docker is what you start with, and Kubernetes if you have like sort of massive scale sort of infrastructure needed. So yeah, I mean, it's basically what it means is like you can sort of define your ML process, ML code, and everything that you have had it on GitHub. So you have that defined in a way that you can create a Docker image. So you can run it in any environment without any problem. So it's a really good practice, and I think it's a must-have if you're a data scientist to have to Dockerize your sort of ML code. So in that way, you know uh, whatever the changes that you did in your environment would work in somebody else's computer. So you might have seen this meme. It worked on my computer, but not yours. It comes from this like because Docker is a solution for that, where you sort of create an environment that very easy to build, and it is not necessarily platform agnostic. Let's say like OS agnostic. It's sort of the user's part of operating system though. But still, if you build your image in a way that can be portable for different, like using BuildX, it's easy to sort of deploy it in like a Unix based or a Windows based or a Mac based operating system without a problem. So so it's important to like go into detail on Docker and to understand like how do you do the how do you build the image. But the underlying concept is you need to containerize your ML code so that you don't have to worry about if it will work in a different environment. So if you do this, it's very easy, and you can use, if you have Docker image, you can run Kubernetes clusters with the same sort of setup. Yeah, read about them if you haven't heard before. It's really useful, and it's used a lot in ML engineering domain. It's similar concept, infrastructure as code. It's basically you sort of, rather than manually configuring the infrastructure needed to run your sort of ML pipelines, you define it as code. So Terraform is one good example, and like AWS has their own infrastructure as code sort of language. You use YAML, and I can't remember the exact tool that you use, but yeah, so you have that as well. Is it Cloud Formation? Can't remember. Could be Cloud Formation. So simply the idea is you will have everything, every resource that you need to run UML or any other sort of code base that you have. You define it as code rather than manually creating it. So in that way, it's very deterministic. So if you see any problems, I mean, if there are problems, you'll see that very easily, and there's audit trail to understand, because you commit this code, and if somebody has done something wrong, you can revert very easily. And yeah, so I would recommend reading about this infrastructure as code. But if you're coming from software engineering background, you'll probably use this a lot. But for data scientist analysts, this would be like a really good start to look at, like, how do you sort of define your infrastructure using code. So it's very deterministic when it comes to at runtime, and easy to like deploy it in different environments if needed, like different accounts if needed. So yeah, that's the sort of the idea behind infrastructure as code. So just before I go into this, do you guys have any other questions? So I take a break here. I guess, sorry, just a question. I guess from like software engineering, or do you have like data science, ML sort of roles, just to understand? Cool. Yeah, so most of these things might be very okay. There's ML engineering, so yeah, Bastian, you might be able to teach me this stuff. So yeah, sweet, awesome, glad to hear. Um, Super. Yeah, I think like, so I think it's very easy for a software engineering sort of person to like get into ML engineering, MLOps, because you have like 80% of the knowledge. Just need to understand like how the model development works, and like what are sort of very unique ML focus sort of tips and tricks. But yeah, it's a very smooth transition. Awesome. So since there are no questions, I will move on with this one. I mean, yeah, feel free to unmute yourself and ask questions if needed. So orchestration. So it's basically like sort of controlling, sort of managing your sort of workflows. So that means whether it's a training process, whether it's like pre-processing, or like how do you sort of serve the models that you've already sort of deployed. So you sort of control how the sort of the ML process works, and things like Kubernetes, Apache Airflow, Kubeflow. These are some of the tools that you can use. And if you go for like more cloud dependent solution, like AWS SageMaker is one good example that you can sort of orchestrate, like using creating pipelines, ML pipelines within that, where you can sort of define, okay, you do pre-processing, do training, do inference, and save the models here and there. So you can, depending, you can write logics similar to step functions on AWS, where you sort of create like the entire ML pipeline using these like SageMaker. So having these your code in as a Docker image is very helpful in this case. So we can easily use one of these pipelines very easily, and you can tweak certain parameters that you feed into the image to sort of get the behavior that you want. So whether it's a pre-processing step, whether it's a training step, etc. So that's the sort of the orchestration piece. And if you are from sort of ML engineering, if you want to get into ML engineering, do read a lot about this. I think this is where I think your value comes into play a lot. How do you do orchestration, whether it's training foundational models, whether it's like doing fine tuning of the models, like things like that. This is where sort of like core of the sort of skills come into play. And yeah, really interesting area, I would say. Yeah, so the next concept is drift in machine learning. Not this drift. It's a slightly different drift. So what it simply means is like you train a model and it changes its behavior due to different external sort of realities. Like, so data feature drift is one example, where what it means is like um, the the input sort of that you use. Let's say you have like a specific type of a world view when you train the model, but it has changed. So it could be like there's a new feature added, like for example, let's say before 2017, if you're training a model in the healthcare domain, you wouldn't have information about COVID. So now, if you're predicting like a patient outcome using some inputs, COVID was not a input, or a prediction, I would say. So now the world will have changed. So you need to sort of factor that in. So any training model that you've done in the past needs to either fine tune their model, like with this new data, or like retrain from scratch. So this is one example. So your initial features that you used have changed, and you need to sort of retrain the model. And concept drift is it's basically what it means is like the relationship between input and output data has changed with time. Just trying to think of a good example for this. Um, how to say? I mean, let's say the COVID example as well. Like, right, in the past, if you have, let's say, cough and fever, you would have certain set of uh, patient outcomes, like certain predictions for what's the reason for that. Now after 2017, like there's another possibility you'll have COVID. So that's a sort of a concept drift. So you have changed the relationship between input and output data. So you need to integrate that into the model. So you have to keep track of, like, obviously the input data that's coming in, as well as the world view, like if there's anything changing. So you'll have to sort of change, um, sort of the retrain the model simply, to sort of factor these in. And then there's model drift, model decay. It's basically sort of, you might have seen on like GPT models, like when they try to like retrain with existing data, at some point I remember ChatGPT sort of like lost its sort of accuracy, probably like middle of last year, I guess, like maybe early this year, simply because I've heard, I don't know, like whether it was the case, um, that you train from like existing data, like without like considering the quality of the data. You tend to like have a model that is not up to par, and so it's very important to like keep track, like whether your model is performing, and you have tests in place to make sure that your model's behavior is as expected. So otherwise model decay happens. So I think like the last line sort of explains what it means between these. Data drift doesn't always result in model drift, but so, and however always indicate that the model's performance is degrading. So concept drift is an example of a data drift resulting in model drift. So that's the difference between these trends. I'll put a link here. So it's about concept drift, and they talked about feature drift as well there. Yeah, go and check that article. It's really good. They have like a really good library that you can use to sort of keep sort of detect drifts in sort of predictions, and also like quite a few cloud providers have services within them to like, detect drift. It's very more important to sort of have this in your pipeline in a way to detect, especially if you have models running long term. You have to sort of keep track of this to understand like the health of your sort of entire pipeline is good. uh, yeah, so it's the next like extension of this discussion, like monitoring and detection in ML. So after like training and deployment is like the first part, but like the problem starts after that. So it's very hard to do, like to maintain a model in infrastructure, especially if you're like a medium or a small scale company. So if it's bigger, yeah, it's easy. You have resources to like build everything in place, like more deterministic systems. But we're starting off like after your first build, like it's a bit of a hard task, but you can do it if you sort of follow like good practices. And you do model monitoring, so that means like you track the model's performance and data quality that's in production to detect drift. So and make sure that the model that you have is doing what it's supposed to do, and then do data bias detection. So as I said, like the input data that's coming in could have certain biases, and that could sort of result in certain skewed model predictions. So you can do fairness detection, and then do like if you see biases, you can do the bias mitigation mechanism. But then I'll give one example that for this one, like for example, um, let's say if you train a model for healthcare data, and you will have, especially, so I live in the UK, so if you use data from the UK, you would have quite a lot of data about white people. So you might not have enough data about from black people or Asians, etc. So if you train a model without considering the bias, the model would perform really well for white people, because there are certain intricacies that sort of applies for white people here. And there are like sort of nuances for if you're coming from a minority race. So when this happens, you have to either sort of like first detect these problems, and then figure out like how to sort of like solve this. Like one is to like sort of do a balancing of data. So either you increase the amount of minority data that you have, or you reduce the data from sort of the people, the white people. So there are different ways that you can do this, but you have to make sure that you're not sort of making unfair for any of the races. But it's very important to be aware of this, and then do certain techniques, ML techniques, to improve the model's accuracy for all the races. So some of the sort of things might not sort of affect the race, but I took race as an example. There are so many other biases that you see in data, and it's important to sort of identify this before you sort of deploy them in the wild. For example, I've seen quite a lot, maybe a few years ago, when you go to the washroom and if you like use the automatic sort of the tap, it might not work. So once I had faced that, like I don't have like a really fast skin, it wasn't working for me. So somebody else, like friend of mine, had to like open the tap. So it's a very simple thing, but the computer vision model, or probably the IR sensor, is not picking up my skin color. So things like this is just a simple example, but like when you have models trained, you have to detect this, and then make sure that it doesn't, especially in critical areas like healthcare or financial sector, you have to make sure that these things don't propagate into production as much as possible. And then do pipeline monitoring, especially see if there are failures, if the training process happen. So you can set alerts, and like, so for example, if you're a developer, sort of an email thread, you can get an update if there's something's not working, so somebody else can pick it up. So things like that. There are really good practices that you can draw from software engineering, that you can plug in to your sort of ML ops process, so that you maintain like a really good health in your system. So there's another article on model monitoring. I'll provide link here. Yeah. And also environment management. So in software engineering, you'll have like test environment, development, staging, production. It depends. Naming really doesn't matter. So it depends on like how your team is structured. But still, the idea is you need to sort of have different environments so that you can test and sort of what's the word, sort of progress, and sort of like upgrade your code and the model eventually to production. So so your development is basically, you do like development, could be a local machine, it could be sort of different environment that is set in a cloud environment. So you have that, and then it could just check just the code logic, right? It might not check how well the model is performing. And then you do testing, which could be the production environment, but you it's not in production, but same settings as production environment, and you might be testing the same development test that you did. And then staging could be the area that you do a full run of your training process and check if the code, the models and everything else is behaving as expected. You'll have tests in place, and then when those pass, you can move to production. And if let's say in production you train a model, and then before the model gets deployed, you can make sure that somebody who has authority over like controlling the model deployment can to do check that and like give the green light to pass this to production. So having these different environments sort of makes life much easier, comfortable, and it's good for the business. Even though might be a bit hard to set it up when you start off, but like with CI/CD on GitHub, it's very easy to like you can have like these tags in place. You can run in tester one, and then move it to staging and then production, things like that. So it's a really good concept that you need to learn, and how you break it down is very subjective to how your team is performing and working. But as long as you have a system in place, that's good enough, and then you can sort of do tweaks. So yeah. The next is testing in machine learning. I think testing is very common in software engineering, but you might sort of expand that into some other aspect as well, like data quality testing. So you want to make sure that data that's coming in is of like as expected. It's not necessarily you would have like a really like 100% perfect data set, but still whether the columns are there, whether the data distribution is good enough, and are there sort of new sort of categorical variables added, things like that. You have to keep track of this, because otherwise your models will break. And whenever that something is not wrong, like you have to like detect them early, so and then sort of address them accordingly. And then model evaluation testing, the basic metrics like accuracy, precision, recall, and then during model training, like cross validation, holdout validation, performance benchmarks. You can use these to make sure the model is good enough to be deployed into the next stage. So you'll have this in different kinds of tests written in machine learning. I think unit testing, integration testing, regression testing is very common, like very familiar in software engineering. So the idea is, so it's a bit of a tricky concept, because I think if you are analyst or data scientist, you tend to work on different notebooks, not necessarily on scripts or like double OP based or even script based sort of approach. So it might be very hard to write unit testing on notebooks, and I wouldn't recommend doing that either. It's very hard. It's very messy. So generally, what I would recommend is like, okay, build your model on Jupyter notebooks, but after that, work with a ML engineer or yourself to convert that to scripts, and then like do like convert them to object oriented programming sort of structure, or some sort of a structure that you could have like methods in place, and then you can like test those methods whenever you sort of um, deploy this, because it's very important that the specific components of your code is performs as expected. And then there are probably two layers of testing this here. Like one is like testing for accurate like code accuracy, and then testing for model accuracy. Like after, so you first do like a easy check on your tester one, that okay, your code is working without a problem, but you need like another layer of testing to make sure that the models that I get trained in these steps are good enough. So yeah, and then you've got integration testing, especially when you have like multiple steps like pre-processing, model training, and sort of deployment, things like that. You have to do like end-to-end tests, like how different components are sort of working together to make sure that it's good enough. And regression testing, I think, is sort of extension where you sort of, if you do like new changes to the code to make sure that the old ones are not breaking, so you do regression testing. So these are like some of the areas that you want to focus on when you do testing, and these tools are very useful. So the Pydantic, Great Expectations, PyTest, very common in Python testing, and you can extend that to machine learning as well. So do check them out. Like it's very useful if you're not using them already, but it's really important that you get your testing in place. ML, like start with something simple, but you add as much as possible as you go. So yeah, that's my take on testing in machine learning. It's really important and saved a lot of sort of struggle, especially like things like data quality check at the beginning, lifesaver. Otherwise, like you'll be training models and you have no clue why the model is not performing well. Then you go back and check, okay, it's input data problem. Mostly it is input data problem. But yeah, So that's why testing is important. And then inference and prediction types. Um, so there's batch inference where you do like you provide like a massive data set, not like a single input. Like you give like a massive file and do like a batch prediction. This is very useful. You don't need to give like real time inference. For example, so one of the things that we do is like predict certain indicators of certain companies. These are needed for reporting purposes, but it's not needed by a specific user in real time. So you provide that information and train the model and then get the results and have that data ready in S3 bucket or some sort of shared folder so somebody can access that predictions. So that's very offline sort of batch inference, or you can use that data and upload it to a database, and the program can use that at real time, but it's you have pre-computed the inferences, so that sort of speed up sort of the inference at runtime. And then online or real-time inference. So predictions whenever you get results. So whenever you do these, it's really important to understand the capabilities, capacity of your sort of server that is sort of providing hosting this service. So for example, if you get like a massive surge, your service could crash and the um the service wouldn't run, so you wouldn't have the ML sort of service running. So auto scaling with things like Sage, AWS, it's very useful here. So that as long as you are a profitable business, not like a hobby project, you can sort of switch it on, and then whenever there's a surge in incoming traffic, it will automatically scale, and this is why sort of Docker images sort of come in handy. You can sort of easily sort of scale really fast without a problem when the sort of demand gets high. And then interactive inference, I think this is it's a subcategory of real-time inference. Things like ChatGPT or anything where you sort of interact with the user and sort of do back and forth and make predictions based on user queries. It's not necessarily sort of one-off sort of prediction. It's a variation of sort of real-time inference. Yeah. And then yeah, deployment strategies in ML. Um, I think CrowdStrike is a good example on how not to do it. I think you might have seen it on news. Yeah, it is a massive failure of like um, deployment sort of issues. You just screwed it up royally. So there are certain ways that you can deploy like changes to your code, like your ML models, like canary deployments, blue-green deployments, rolling updates. So these are different ways, and I think companies should have some mechanism that sort of considers this. So canary deployments are basically you rolling out new models to a small subset of users or traffic to minimize impact and gather feedback. So in that way, you can see if something is wrong rather than deploying everything to everyone. Blue-green deployment sort of you maintain two identical production environments, calls in blue and green, and switching them between zero downtime updates. So like you build a sort of a other production environment with the latest update, and you do the switch. This is a bit of risky move, but still, as long as you're tested and like you've done your sort of testing with your code, you can switch very easily, and we can switch back if needed. Rolling updates, you do gradual updates to models across servers or instances to ensure continuous and minimal disruption. So you can select like specific set of servers that you want to update, you update them and see like how well they're performing, and then do like gradual updates. Yeah, so I think there are quite a lot of variations of this. This is still a very, I would say, theoretical categorization. So there's quite a lot of nuance when you go and implement this in your sort of environment. But the idea is like not to like deploy everything at once. Make sure that it's tested and as well as it's gradual to see any issues, and then sort of do the deployment. So that's like the sort of the high level, sort of the base with regard to deployment strategies. So just want to make sure that you get that sort of concept in. Yeah. Yeah, I think we are at the end. We discussed these concepts today, and yeah, so would like to sort of get your feedback as well if you got some time. Just I'm doing a bit of a survey just to understand like what sort of areas you'd like to learn more, like to create sort of my next sort of content as well. If you got some time, feel free to fill that up. I can check voting as well on that. Yeah, I mean, if you guys have any questions, do let me know. Happy to answer them. You got some time left, I think. We almost at time, but I'm happy to answer if you have any questions. Yeah.
I had one question. So, I was trying to understand more on this part. So, when we train or test, we get certain sort of accuracy that we talked about. But how do we translate that to the inference time accuracy? Like, so we are aware that during training and testing data set whatever we had, we were getting certain accuracy data points.
Hmm.
But how do we ensure that during inference we are maintaining?
Okay. So if I got the correction question right, it's basically um, you maintain like in testing we'll have like cross validation to test accuracy, and real time when you deploy it, like how do you measure accuracy of your model, right?
Correct. Yeah.
Yeah, so I think there are multiple ways to do this. Yeah, I think uh, obviously one simple concept you might have seen is like getting user feedback. Like for example, if you look at ChatGPT, it probably asking you like, okay, how well this prediction did. So you can gather feedback like that. So, but if it is a um, tool that doesn't have sort of interactive sort of chat interface, you want to consider other sort of metrics to make sure that the prediction are working. For example, if you take Facebook, it could have a service that predicts your predict friends that to send friend request. Even LinkedIn has this, and see the number of clicks that you'd have on that predictions and how many of them uh, went on to become friends or connections. So that's an indicative indication of how well the prediction was there, and you have to keep track of this and do a sort of pre-processing calculation with this information to see, okay, you have the prediction and this is the outcome of that, and then you can do pre-processing to see, okay, this model is performing in this way. So it's not like very similar to test what you do in testing, sorry, training space, but it's more of a sort of a context dependent and business and domain dependent sort of approach, and you have to define it that way, like what sort of metric that you should track to come to the conclusion, okay, whether my model is performing well or not. So I would reverse engineer from like sort of why you're building the machine learning model, like what's the business metric that you're trying to improve, and then see how to measure that metric, and then measure that metric and sort of see if how well the model is doing. So that's one way of how to do it. And you can also keep track of input data that's coming in, like different sort of interaction that you have with the model, and those also give indicative of your model is behaving well. Did that answer your question?
Yeah. That totally answers.
Awesome. Yeah, Cameron, go ahead. Yeah.
Hey, thank you for the presentation. Lots of different information on MLOps and lots of things I'd like to explore further. My question is, so in software engineering right now, I'm seeing a lot of code generation tools like
Mm.
Cursor. Replit just came out with an AI agent, and like these tools, I imagine over time will get better with more data and better foundation models. So there's I do feel a bit of like existential anxiety about like, automation and software engineering and the potential. I don't know how things are going to play out, but potential for reduced need for software engineers in the future. Like one software engineer can do what it takes 5 to do today or whatever. I'm just curious, in ML engineering, do you see that same thing sort of happening, or do you have any perspective on that as far as the role, I guess, of code generation in ML engineering?
That's a really good question. Yeah, stuff that I think all the time. Yeah, I think like any other industry, it's gonna get disrupted a lot.
Mhm.
And even in like ML engineering, software engineering is gonna get disrupted, and like because it's a matter of sort of demand and supply, right? It's just economics. And I think how I would go about this is like if you're ML engineer, software engineer, like how I look at it is like you have to get upskilled in these tools no matter what, like and some of these might not be practical. I think like I've seen like yeah there's a hype, but after 2 3 months the very specific use case is not generalizable. So that's the downside of this, but still it's the people who like you might have seen this code like it's AI wouldn't replace you, it's just the person who's using AI would replace you. So basically the idea here is like as long as you learn these tools and like use that to improve your productivity, and it's going to be it's a game changer and you don't have to worry if you do that. So like people who understand the fundamentals like DevOps, MLOps, like software engineering, machine learning, as well as if you can use these tools really well, whether it's chat GPT or like agentic IDEs that's coming up, um, and it will sort of 10x your productivity. So in that way you can get more throughput as an engineer, and yeah sort of keep learning. And after, I think it's very hard to predict like where it's going to go. So I think that's everybody's idea. But you are at a certain level, right, like you are probably at like 1% of engineers in the world. So in that regard it's fine, but you just have to keep pushing yourself to become better. And I feel like after a couple of years it comes sort of equilibrium. It's like these tools, like we'll have set of tools that easier to use and more productive. And then yeah that's how I think about it, like so I learn every day like different concepts and different tools. And there's another sort of IDE I was trying out, Cursor, I think. I mean it's not very new, but it's I think AI based sort of IDE. I found it interesting that it's much better than VS Code, because it's a VS Code sort of a extension, sorry, not extension, VS Code based IDE. So it's very similar to VS Code, but it's built in a way that you can sort of easily integrate uh, AI workflows within that, so to code generation, write test cases, etc. So things like that, sort of keep an eye out for those kind of things and sort of integrate them to your workflow and see. I think that's how you go about it.
Okay, yeah, that makes sense. Thank you.
Sure, awesome. Go ahead, guys. Yeah, listening. Yeah, sure.
Yeah, thanks for the presentation. It was really complete. I had a question on the orchestration tool. How long do you wait in a project to start adding this orchestration tool? Because they can be quite complex, for example, with Kubeflow. And do you start right away or do you wait a bit to use them?
Yeah, I think that's a really good question. So I think I would first try to get like, so it depends. Like if you have other projects running your organization, it's fine to start with the orchestration. So for example, infrastructure needed, so those two can run parallel, setting up the orchestration and new model development. But if it's a new project that you're running and we don't have any sort of blueprint, I would just get your model working right. And then after that, you build the orchestration around it. But I feel like with your context, you might have already orchestration set up for different projects. So I would do it parallelly so that you can sort of see certain changes in the code, the model development phase that is needed. Because if you start building from the code, model from that, the code might not be sort of easily transferable for the orchestration sort of process. So that's how I'd go about it. Another thing to consider is that like the type of orchestration that you want to do, it depends on the composition of your organization. Like if you have like it's a heavy data science team, like very few engineers, you have to sort of cater for their user experience. Like how do you sort of make sure that the data scientists are able to get the best of themselves, like model development aspect. Like so you do the orchestration in a way that it's helpful for them as well. So that's another dimension to consider. But yeah, I mean I'm definitely trying my best to like have a discussion, at least if it is not possible, to how to do the orchestration when you start the project, because otherwise like the code development sort of like go in a different direction, and you'll have to spend a bit of time to like sort of shape it into a way that you can put it in the orchestration pipeline. So yeah.
Okay, thanks.
Yeah. When you go ahead, yeah.
Yeah, hi, Ashika. Great talk, first of all. I'm a early to mid-level software engineer, and like Cameron pointed out, I have this constant fear that AI is going to replace software engineers one day, and that's one reason why I started learning about machine learning.
Yeah.
And for someone like me who's just getting started in ML, my question is: so I see this Google has this professional machine learning engineering certificate. And I believe Azure and AWS also have their equivalent versions.
Yeah.
For someone who's getting into ML and who's trying to get into ML roles, switching from software engineering to ML or something like that, does a certificate like that add value, or is it better to work on projects and Kaggle competitions and all that?
Yeah, I think it's a good question. I think, let me think. Given your background, like because you have like a really good experience in software engineering, I think it's best to go for a certification. I wouldn't recommend this to like a lot of people, but I think it's good if you go through, like, because you haven't had that kind of sort of background before, I'm assuming. It's good to go to a structured sort of a targeted either a course or a certification, so that you get the basics right. So otherwise you might go in certain rabbit holes. If you do a Kaggle competition, you go in depth for a specific topic, but you might miss certain like sort of like breadth, I would say. So I would go for some sort of a certification like that. I don't know about the Google certification much, so I don't know like to recommend or not, but I think I've done AWS certifications; those are really good. So as a starting point, and then like think about doing projects. I would say whether it's Kaggle, whether it's like mini project that you do on a weekend, hackathons, like you do after you have the fundamentals, like go on to do that. Like, even like I would recommend like doing a talk like this. Like for example, if you want to like learn a specific topic, like set a time on Taro events and make sure that you sort of go and do that, so that it makes you like sort of gets you to do this kind of like teaching aspect as well, so you can teach different concepts. But I would start your fundamentals like with some sort of certification. I would recommend that. Yeah.
Yeah. I'm not new to the fundamentals. So I worked for a couple of years and then I pursued my master's. I just recently graduated, and throughout my master's, I did take a couple of fundamental ML courses. And machine learning being a very deep field, I would need a PhD if I want to learn it in depth. But with 2 years of master, that's how much I could study. So I think I have the fundamentals right. I constantly read blogs and books, but
Yeah.
I still don't know if I have everything that is required to be an ML engineer. So that's why I'm asking.
Yeah, I don't think like anybody can like learn like what's coming out these days. So it's very evolving field, and like especially in the last couple of years, there's quite a lot of attention in this space. So because there's a lot coming out, so it's very hard to keep track. So I would pick a domain then, like for example NLP or computer vision, like whatever you like, or it's like the infrastructure, like the training side of things, like GPU training, etc. So and then sort of like see what you like, and then sort of go deep, like make a bet on that, like go deep. It wouldn't go wrong. I would feel in the next 2 to 3 years, whether it's, I'm sure like quite a lot of it, like training sort of engineers are needed to do training, and like quite a lot of applications in NLP, like how do you like sort of do fine tuning like large language model, like with open source models. So that's another aspect, like even for computer vision, like, so pick an area that you like and like sort of go in deep. So if you're going for the infrastructure side, like it's best to like learn some sort of a infrastructure focus certification and do projects on that. And if it is like more application side that you want to focus on, pick NLP, computer vision or time series, and then sort of go deep in that. So that's how I would go about it, and don't worry too much like that, because the level of that anxiety that you have is shared by everyone. So like you at a certain point that is like the top like 1%, so don't worry in that sense. As long as you're like, the fact that you have this feeling, that means that you're like feel the pressure and you're sort of learning, so that's good enough. So that's like, you just keep at it. I mean, that's a sign of that you're learning. So and you don't need a PhD to do like in-depth ML, right? So I mean, uh, don't I don't think like you should think like that. I think the master is more than enough to go in depth. And yeah, it's just, I think after like fundamental level of calculus and like certain sort of linear algebra, ML is quite easy, I would say. But yeah, it's more like exposure that you get after that, like projects, like different kinds of projects that you do. Like, I mean, I do consultancy to make sure that um, I get to solve problems that are like very unique and very business focused, so that I'm up to date. So that's another area that you can try out, do consultancy, so that you get exposed to real ML problems rather than Kaggle type of problems, which are very data sets are very clean, and like you have like discussions going on, which is helpful to start off with. But I think eventually you need to be in like in the wild and like sort of tackle problems and in real business settings. So that's where the companies would value you more, like so you can like solve problems in like of that nature.
Got it. Got it. Makes sense. Thank you.
Sure.